Okay, the second part of section 6.2 on electrical losses, we're going to explore a little detail on brush losses and iron losses. Before we do that, let's look at this equation for losses expressed per in watts per kilogram. So I've got a figure. I should have shown this to you in the first one. Let me show you that right quick, and we'll move forward from there. So here's our equation 6.3 that gives us the loss in kilowatts or watts, I guess I should say, right? Watts per kilogram of material, and this is a certain example, that has a square centimeter of material, 200 amps. In reference to the current that's flowing through it. And we talked about current density at 80 degrees C, which is just for, the temperature. And then that this is a copper conductor, okay? And again, we'll revisit that more in a specific problem where we do the calculation. And then for brush losses, the I squared R losses in the brushes are pretty small, because the current density is only about 0.1 amp per millimeter squared, which is much, much less than what you would have in the copper itself. But the contact voltage drop between the brushes, and the commutator may produce significant losses. So there could be a voltage drop from 0.8 volts to 1.3 volts, depending on the type of brush, how much pressure is applied, pretty complicated considerations there that you're looking at for that. But, here again, we just want to recognize the occurrence and, the fact that we do have a method of quantifying that if we need to. All right. So then the last thing that's discussed is our iron losses, and they're produced in the armature of machine. They're due to something called hysteresis and eddy currents. Eddy currents occur in material because they're exposed to a magnetic field. Okay, so this exposure to the magnetic field causes these internal currents to be created. And then, those currents cause heat losses. And then hysteresis is this effect of alignment of the molecular structure of the material and sort of this lagging effect that occurs. It's hysteresis. I hope you've seen that or been exposed to that in things earlier. But he tells us that the iron losses depend upon the flux density, the speed of rotation, the quality of the steel, the size of the armature, right? So very, very involved calculation. They typically range from 0.5 watts per kilogram to 20 watts per kilogram. And, he says that these higher volumes occur in the armature teeth, where the flux density could be really high. He says 1.7 Tesla, which is a high level of flux density. The losses in the armature core are much less. And he goes on to say that that these losses can be minimized through an annealing process, which is really a heating of material under controlled conditions based on the particular material that you're seeing. And this is, here are some laminated plates that are going into the construction of a generator or a motor, and they're being annealed through this heating process. And, that's something that helps to minimize the iron losses. And then some iron losses they happen in the pole faces themselves. And it's kind of interesting. He says, as strange as it may seem, iron losses impose a mechanical drag on the armature. These losses that are occurring in the material actually produce a mechanical drag on the armature. And this effect is the same as the effect we would get from a mechanical friction. So, you know, sort of an interesting thing that's going on there. This mysterious magnetic field and all the things that it does is sort of interesting to follow. Okay, so let's work through a problem. Let's work through example 6.1, and we'll go through that and move on to the next thing. So in example 6.1, it says I have a DC machine that is turning at 875 RPMs. He tells us that the armature winding has a total weight of 40 kilograms, that the current density is 5 amps per square millimeter, that the operating temperature is 80 degrees C, and that the iron losses are 1100 watts. So he says, calculate the copper losses and calculate the mechanical drag due to the iron losses. In other words, we're calculating the iron losses. And by the phrasing of that, recognizing that it does result in a mechanical drag. So what we need first is we need to get the resistivity based on this particular temperature that we're at. So we're going to take the resistivity based at 0 degrees, and we're going to plug it into our equation, 6.2, and it looks like this. We put our numbers in here that we need. We find 15.88 from the appendix 2 that we looked at earlier, then 1 plus, then we also find the coefficient that we need. Let's see, how's he writing that? 0.00427, and that is multiplied by 80, okay? So all of that's going on there. And then this 15.88 is in nano-ohm meters in the table. Let's see, what else do we know? We multiply that through, and we should come up with 21.3 nano ohms per meter. All right, so again, that just gives us a value that we can use in this. Now, let me pause this for a second and let me show you these values in the table. Make sure that you're able to find these, because this will be one thing that you'll need to be able to do, you know, is to utilize the table to find these values. Okay, so I've got the table here in front of you, and here is the two values. Okay, here is the copper at 0 degrees C. All right, that is this, and then here is the temperature coefficient at 0 degrees C that we need. And notice that it is times 10 to the -3. So that's where, you know, this value that you're plugging in is 1, 2, 3, the 0.00427. And this is in nano ohms. All right. So that was, you know, that was what we were plugging into the equation. And I just want to make sure that you get that. And then, you know, not to, you know, make it too simplistic sounding, but, you know, how would we know? Okay, we're trying to find electrical properties, right? So, you know, if we're finding electrical properties, then, you know, that's why we're using this value, and this is the type of problem that we're solving. And, you know, you need to be able to find these values in a lookup chart, you know, to plug into the equation. Okay, so now I'm back to showing you this chart one more time. The reason I'm doing that, I'm not sure this is crystal clear here, but you know this this density value that we need in this, that, you know, represented by this lowercase zeta, which I even have a hard time drawing. You know, we're dealing with copper again. You know, here's our you know, line of values that we're looking at in terms of electrical and mechanical thermal properties. He's asking for density. We don't see that symbol given to us in that column, but, you know, it was given to us as kilogram meters cubed, And so that's where this 8,890 comes from. Okay, so just wanted to point that out right quick before we finish this problem that we're working. So when we get back to the problem here, we know that the density of copper was 8,890. You know, we got that from the table. And now we can plug in. We've got 1,000 times the current density, which is, you know, we just need the number 5. The resistivity that we got that's referenced to our particular temperature was 21.3 nano-ohms, and that is you know, make sure that you realize in this equation that that value is given to us in nano-ohms per meter. Okay, now in the equation it does this, and you know, it really should be this. Okay, and that almost looks like Newton meters, you know, with small numbers. But if you look back at the original way that equation 6.3 is given to you, and he gives you what resistivity is, it just says this in the text, but he's really talking about the equation is written in terms of nano-ohms. So you know, that's why we want to leave it that way. And then this is divided by this. Okay, so you know, plugging in here and getting the value out of this, I come up with 60 watts per kilogram are the losses for this. Okay, now the thing is, are we finished? No, not quite. The total losses, since it's 60 watts per kilogram, we're told that the armature winding total weight is 40 kilograms. So I've got 40 of these 60 watts, 40 kilograms, times 60 watts per kilogram. So if I multiply that out, that's where I get the 24 and 2 zeros. 2,400 watts would be the total copper losses from that. Okay, now, second part of this, something that, you know, how would you get there with this? You know, this is, you know, just something, you know, that's what we're doing, right? We're learning, but he's asking for what is the mechanical drag. All right, so actually, you know, and this is really a stretch, isn't it? We have to think of this as a braking torque. Wow. And so that goes back to this problem, you know, power of a motor, solve for torque. All right, and I contend that that's not necessarily an easy thing to find, right? You know, that is a stretch for us to get there. So that's, you know, make sure that you catch that in this particular problem. So we would be saying 1,100, and the 1,100 comes from this given of 1,100 watts, and we're trying to get the torque that these iron losses cause on the armature, the braking torque, the drag, in other words. Okay, and then it's at 875. We were wondering where that was going to come into play, right? And so that's the speed. T is what we're solving for, divided by 9.55. Okay, and then we run this through, and we get a value of 12 Newton meters of braking torque, which he says is approximately 8.85 foot-pound force. Okay, if we needed it in that form. All right, so the main thing here, take away from this, that these iron losses actually produce a braking torque in the motor. Okay, that's an interesting thing to consider as we go through this. All right, we'll wrap that up and move on to some things that are definitely a little simpler, and finish this chapter up.